Final thing we need to talk about are multidimensional arrays. So we've talked about linear information. We've talked about storing information sequentially, thus Python sequence types, right? But this isn't really perfect, right? We might want to store tables of information. We might want to store things that have rows and columns. So many programming languages allow for multi-dimensional arrays, and these are most commonly in the form of a two-dimensional array or a matrix, like, say, this, right? The first dimension defines the row. Second dimension defines the column, right? And you can see that conceptually numbering starts at 0, 0 in the upper left and expands down into the right. Okay. Anyone who's worked with a graphics package of any sort, and those of you who have taken CISC 120 recently will know that graphics packages typically start with the upper left-hand corner pixel of your canvas being 0, 0. And this is why the graphics package stores pixel information as a two-dimensional array starting in the upper left-hand corner. So when you are talking about, hey, change this pixel in this row in this column, what you're really doing is changing the RGB value, not to be confused with the RPG value, rest in peace, the RGB value of the pixel at whatever row and column you're talking about. Okay, so that's why, I know we all think, well, this doesn't make any sense in a standard, Cartesian plane. 0, 0 is in the lower left corner. Well, this is why. It should be noted as well that three-dimensional or higher arrays are possible. So I've definitely used three-dimensional arrays, and I think I might have even used a four-dimensional array once. We can think of three-dimensional arrays conceptually as basically, okay, now I've got a bunch of these tables, right? The third dimension is which of these tables going back into my filing cabinet do I have? And the four-dimensional array, well, unfortunately, we cannot think of this conceptually, but think of multiple drawers of three-dimensional arrays. So I am serious. You do see these sometimes, but most times that you're going to use a multi-dimensional array, it's going to be a 2D array. Indexing is done just like an array, only with two indices. So you give your, if this table is named, if this 2D array is named matrix, you go row, column. That's it. So if we have matrix 2, 7, what do we get? Well, we can come down and we can see, okay, row 2, right? Column 7. And I believe this is going to highlight in a moment. But for those of you playing along at home, I wanted you to be able to see now. And this can be done for reading or writing. So we can say matrix 2, 7 equals if we want to write to that slot. Or we can say something equals matrix 2, 7 if we want to read from that slot. It is just like a standard list or array, just done in 2 dimensions. In Python, a matrix really is a list of lists. And that works just like a 2D array in other languages, but what do you think is going to happen if we do the following. Let me open Python. Yeah, that'll work. All right. And we're going to say, here, we will define it this way. We'll say matrix equals, and we're going to make it a list of lists. So we'll say 1, 1, 1, 1, 1. Okay, so we're going to have 4 columns. 2, 2, 2, 2. And we're going to have 3 rows. 3, 3, 3, 3. And we can see if we type out matrix, it looks just like that. And if we say matrix 0, 3, right? Row 0 with the elements 1 in it, give me the last column. Because we got 4 columns, index 3 is the last column. Okay. What do you think is going to happen if with this code we then say, you know what? Let's append X. Matrix 0, append X. What do we think is going to happen? Well, remember, the computer does exactly what you tell it to do. And this is a list of lists. So when you say matrix 0, you get that list. And because this information is stored referentially, right, the matrix itself is storing a reference to this list. So when we say matrix 0 dot append X, it does. And now when we say matrix 0, we have X at the end. And now when we say matrix, we have X in that matrix. So it does exactly what you told it to do. It just appends X to the matrix at the row that you ask it to. And this is what's called a jagged list or a jagged array. And we can see that jaggedness if we print out, if we say for row in matrix print row, right? You can see how that one row sticks out. So that's why it's a jagged list or a jagged array. It's not ideal. Now we can't iterate across the columns easily. I mean, we can do it independently. You would have to find the column number for each row. You can't just say, oh, I've got a what's that? 3x4 table. You can't do that. So how do we make an empty matrix? Well, we can answer this question. How do we easily make an empty list? And when I say empty, what I mean is I would like a list with a certain size. Let's say n, because n seems to be convenient. But I don't want any information inside, right? So in Python, no information is none, right? And remember, we can easily do something with any sequence value. Remember that multiplication will repeat a string, right? And make our terminal say what we feel this year. Ah, right? That's real easy. But a string is a sequence, like a list. So if we said this, we can say hey, look, we now have a list of size 5 with none in it. So that's cool. That's how we make an empty list. We just do that. And a matrix, a multidimensional array, is just that, right? It's just a list of lists. So we could do something like, oh, I don't know. We could do something like equals, let's do our none here. And we're going to multiply it by, we're going to say 3 rows. And then, so we're going to have, I'm sorry, that we need to do columns first, right? It's going to be C first. And then we're going to say, because that's going to make our list. It's going to make 4 nones in a list. And then this is going to make 3 rows. So we can do that. Oh, that doesn't work. Oh, that's right. Because what this is going to do, what this does is it really says, okay, now I've got this list, but I want to just repeat that list. So give me a new list. So that it doesn't, you're not explicitly making a list, so this doesn't work. So let's explicitly make this inner thing a list. Let's give it this thing. Okay. Let's give it that thing. Let's do that. And now we can see that it works, right? And we can say matrix of 0, 0, and we're going to set that equal to 1, and that works. And we check our matrix, and we've overwritten all 3 matrices, all 3 lists in our matrix. Why? Why do we get this? This seems broken, doesn't it? Well, let's think a little bit about how this is working behind the scenes, right? When we create this little row here gets a memory address, right? And we're saying repeat that 3 times. This is repeating the reference 3 times. So what we're doing is we are creating matrix 0 is matrix 1, right? Matrix 0 is matrix 2. All we're doing is copying the reference. So we're not even doing a shallow copy. We're doing an alias of that row. By the way, fun fact, because this will mess you up, if you ever define a function or a method with a default value as a list, for instance, sorry, and then you say in that function you do something like, say, data dot append a, and then you do print data. So you define a function where you have a default parameter that is a list literal, and then you alter that list in some way during the function. And this works for parameters too, right? So we're going to call fun1 with the default parameter, and it should be a list with A printed out. And it is. And we call it again, and it keeps adding to it, because much like with our matrix here, right, where we are saying create this list and repeat that reference 3 times, when this function is defined, this is given a reference. And that reference is never altered. So if we were to go back and redefine this function, and do the same thing, but then also print out the memory address of the list ID hex print, right? D60288. D60288. You can see that the memory address of that function, of that default parameter stays. So, similarly, we have the same problem here. Each row ends up pointing back to the same memory address. So if you want to do this for real, we have to ensure that each cell of the primary list, each row, points to an independent instance of a new list. Okay? And the best way to do that is this way. Okay? Now this looks gnarly, but let's walk through it real quick, right? We said we want to do, I'm going to pull that matrix definition up. There we go. And we want 4 columns. And we want 3 rows. So we're going to say 4 J, we'll do I because I like that better, in range, and we want 3 rows. Got to get rid of that. Yeah, this looks good. Okay. And now we can look at matrix. That looks good. We can come back through here. That looks good. And show me the is. Nope. And just to be safe, because transitive applies the one way but not the other way, all 3 of these are different lists and everything works. So I hope this makes sense. I hope you can see how we would roll through this, right? If we wanted to print everything out, we could go for row in matrix, right? For col in row, right? And this is designed to be user-friendly, right? Hey, for each row in our table, hey, for each column in our row, hey, let's print the thing at that column, right? So you're going to notice that pattern when you want to process a multi-dimensional array. Hint, unconvincing cough, hint. There's lots you can do with this. Play around with this. This is going to be super useful for you and is going to be the basis of a lot of information that you're going to end up using when you code, or at least the processing algorithms like what we just did here is going to be super useful as well.